Okay, the goal of this presentation is to try and describe the various IPv4 BGP inter-AS traffic engineering cases that exist today for v4, and to try and put those forward as a straw man for requirements for IPv6 multi-homing solutions. So hopefully this will help define additional operational requirements for v6 multi-homing solutions. So I guess the first place to start is to talk about what is the conflict between IPv4 and IPv6. It's important to recognize that IPv4 very strongly, in terms of stewardship, is very strongly in favor of good use of the space, being efficient use of the space. With v6, it seems that we have lots and lots of space, much like we did in the v4 world in the 80s. And the efficient use of space is not really important. Instead, what's important is to aggregate the space, because we don't want to see many, many de-aggregates in the routing table, because there's huge potential for the routing table to grow. So because of this, IETF and the regional internet routing registries basically have put forward policies that say you really need to announce only a single aggregate. And in order to make multi-homing work in v4 today, you de-aggregate. In v6, they're trying to find a multi-homing solution that does not require de-aggregation. But the problem with this is that if you don't de-aggregate, then you lose routing information. So how do you still do multi-homing and traffic engineering without this additional routing information? There's a number of places where IETF requirements are defined. RFC 3582 and draft IETF multi-6 v4 multi-homing 03. These talk about the need to have failover. They talk about the ability to dial traffic around a bad link. There's some talk in here about being able to policy route and to shift traffic around a performance degradation. But even with these requirements defined, I maintain that there's still no clear IPv6 multi-homing solution that supports all of the IPv4 current cases used today. So what are those cases? There's three basic flavors: primary backup, load sharing across all of your links, and the concept that you're using the best or shortest path between the source and destination. In addition to these three cases, there's the additional requirement to be able to shift traffic around in any of the three cases. So that way, if you have a link that's overutilized, you can migrate some of the traffic away from that link. The fourth thing I want to point out is that these three cases are actually the building blocks, and they can be combined together in very interesting and complex ways. So case one, primary backup. What is this basically? Here the idea is that you can designate a link or a set of links to be primary, and other links or sets of links to be backup. So basically what should happen is the primary links should carry all the traffic. The backup link should never carry traffic unless all of the primary links fail. The common reason for a primary backup configuration is simply a matter of expense in terms of the links, and you can measure expense in different ways. It could be the cost of the link in terms of dollar value. One link you might be charged per packet, the other link you might have a flat rate, for example. Could be cost of the link in terms of latency. One link might have much better performance than the other, so you want to try and use your better performing link first and then only fail over to your poor link. Could also be bandwidth as well. So the way in which this configuration works is different depending upon whether you have a single AS as your upstream or multiple AS as your upstream. With a single AS, the way you can do primary backup is to set either a high med on your backup path or a lower med on your primary path. In the case here that I have shown, I'm showing two different ASs. In this case, a multi-home customer is advertising a /23 to both providers. On the backup link, they're setting a BGP community, which will be interpreted by the ISP to set a low local pref. On the primary link, they're just doing a standard announcement. So what will happen is this will draw all inbound traffic across the primary link. For outbound traffic, that can be done a number of ways. You can have weighted static default routes. In this case, I'm learning a default route via BGP from both providers and setting either a high local pref on the primary link or a low local pref on the backup link. The second case is load sharing. And basically what you're trying to do is to load traffic on all of your links and to try and get them as heavily loaded as possible without negatively impacting individual traffic flows. And typically why people are doing this is to try and squeeze as much bandwidth out of all of their multiple links. And there's many reasons why you might want to do this. One case is where larger links are cost prohibitive. You may be in an area of the world where large circuits are unavailable or very expensive, or you might be a small company who can't afford to go from a DS1 to a DS3. So inbound traffic in this case is basically manipulated by having more specific as well as your aggregate announcements. So in this case, what the Multihome customer has done is he's divided his /23 into two /24s. He's advertising the /23 to both upstream ISPs. He's advertising only the top half to UUNet, MCI, and the bottom half only to AT&T. In terms of outbound traffic, there's, and this will basically draw traffic to the top half of the 24 across the UUNet link, traffic to the bottom half across the AT&T link, and if either link fails, the other link will pick up the traffic. For outbound traffic, there's a number of ways that you can do this. You can have equal cost static routes. You can simply learn a static default from both providers, and that will also work. The third case is the ability to use a non-random best path, and I qualify this by saying for some definition of best. The current definition of best is based on the BGP routing table information and is determined by the BGP path selection algorithm. The important point here is not that the best path is determined based on routing information, but that it approximates the shortest path between the source and destination. In this case, inbound traffic is manipulated by learning a full BGP table from both of your providers and simply allowing BGP to do the right thing. And same for outbound. Outbound traffic, you advertise the same announcement to both of your upstreams and let the far end make the right decision. The fourth requirement as it applies to the first three is the ability to dial traffic around. And basically this is because BGP lacks a congestion control mechanism. Now I'm not suggesting there should be a congestion control mechanism. That's not what BGP is designed to do. But since it does lack one, people have invented ways to kind of shift traffic around so that they can draw some traffic away from overutilized links and onto underutilized links. So I'm going to go through the three cases and show how traffic dialing applies to each of them. In the first case, you have a primary link which is becoming overutilized. So what you want to do is try and migrate some small amount of traffic off of the primary link onto that more expensive backup link. But you want to try and migrate as little as traffic as possible because you want to keep most of your traffic on your primary link. Case 2 is very similar to that, where you have multiple load shared links. In this case, you might have one or more of your links running a little hot. So in this case, you want to migrate a small amount of traffic towards the underutilized links. The way in which you do this is you try to draw traffic to either the backup link or some of your underutilized load shared links by advertising some more specifics across that path. So basically what will happen is, much like the load shared case, you simply divide up your network differently. So you might advertise, instead of a 24 and a 24, you might advertise maybe a 29 across one of your links to draw a little bit extra traffic. For outbound, you've got basically two choices. One choice is by doing some dialing of your IGP metrics to try and make some sources a little bit closer to one of your exit points, assuming you do have discrete exit points. The other way you can do it is you can listen to some of your specific inbound prefixes, pick some routes and distance them so that they will be more preferred across particular outbound paths. In case 3, it's a little bit more complicated because basically what we're trying to do is we're trying to get everybody on the internet to use the best path. But your one best path maybe is getting overloaded, so you want to migrate some small amount of traffic to your underutilized link. But in this case, you're being very particular about the traffic that you want to migrate. The traffic that you want to migrate is traffic that is fairly close to both your best path and then your second best path. So somebody who's very close to your best path but very far away from your second best path, you don't want that traffic to migrate. The way this is typically done is by doing AS prepending. If that's not granular enough, then you can also do additional, more specific prefixes announcements like in the previous case, but that doesn't necessarily follow the best path, next best path rule. Outbound traffic is manipulated in the same way as the previous case. The final point I wanted to drive home is that it's not just primary backup, load shared, and best, but you can have very interesting combinations of the two. In this case, imagine you have a customer who has connectivity to two ISPs, say UUNet and AT&T, and the customer wants to use best path, meaning a source customer who's closer to UUNet should come across the UUNet links. A customer who's closer to AT&T should come across the AT&T links. Now also imagine that the connection to UUNet consists of a pair of primary links and a pair of backup links, while the connection to AT&T consists only of a pair of primary links. So this is a picture of kind of what it looks like. The way in which you want to manipulate your traffic is first by advertising the /23 to both providers, so that way people on the internet can simply choose best path. In order to get the primary backup configuration with UUNet MCI, basically what you'll need to do is, if you have a single multi-hop BGP session for your two links, or if you have multiple BGP sessions, for all of your primary links, you basically have to set a MET of 0 or allow the default MET of 0 to be your behavior. On your backup links, you want to set a higher MET value. So basically what will happen in this configuration is any traffic reaching UUNet MCI will choose both of the primary links. Unless they both go down, then it will roll to the backup links. Traffic hitting AT&T will use both of the primary links. If all four of the UUNet links go down, then traffic will roll to AT&T. If both of the AT&T links go down, traffic will roll to the primary links at UUNet. And if both the AT&T links go down and the primary links to UUNet go down, everything will roll to the backup. So I wanted to talk a little bit about how IPv6 multi-homing solutions that are currently on the table are very different and how they don't support all of these cases. There are a number of solutions that have been proposed. Many of them have expired. LIN6, HIP, MASP, SHIM6. In general, they're all a very similar solution. And basically what we're trying to do is do multi-homing that does not rely on deaggregation. And the way in which you do that is by separating the locator ID from the upper layer ID. All right, so what is this concept of a locator ID? A locator ID is basically the IP address that's on the interface of your host. It's what routers use to route traffic. And in IPv6, you have to have a unique locator ID for every upstream ISP. So that means if you have a host, a web server, for example, that's multi-homed, you have two upstream ISPs, you need two IP addresses for that host. The upper layer ID is the address that the upper layer protocols like TCP or ICMP use to communicate with each other. And the reason why this is kind of strange for us to think about is because in the IPv4 world, the locator ID and the upper layer ID are the same thing. It's that single address you have on your interface card. However, you need to separate them in v6 because what you're trying to do is build the TCP session between an upper layer ID and then have some mechanism to switch out the locator ID so that if there's a failure, you can choose a different destination or a different source. So I'm going to focus in on the L3 shim approach. It's very similar to some of the other approaches, but this approach basically says you need one unique locator ID or IP address per ISP, and you also need a upper layer ID. There's a lot of debate about how you choose an upper layer ID and what it should be. Should it be globally routable? Should it be globally unique? Does it need to be routable? Can it be a cryptographic hash? I'm not really going to address those issues, and I think that that's going to be in the next year or so. They're going to figure out what's the best solution. I'm just going to talk about what SHIM6 specifies. And basically, the way it works is if you do a quad A query, the DNS server is going to provide back a list of locator IDs or interface IP addresses for that destination. And the important point to note here is that list may not be complete. The source will choose one of those addresses at random and attempt to build a TCP session, for example. If that session establishment is unsuccessful, he is then required to try another address. Once the upper layer communication is successful, then the end host can both signal that they're multi-6 capable, and if they are, they can pass a complete set of locator IDs between the two endpoints. And once that complete set is passed, they can then insert the shim6 header, and all of your TCP sessions can switch over to use the upper layer ID as where the TCP conversation is terminating. So just to give you a quick walkthrough of how this works, on the left here I've got a source that's got 3 upstream ISPs. He's got 3 IPv6 addresses on his interface. He's communicating to a destination who's got 2 upstream ISPs with 2 addresses. He does a DNS query. He picks one of the addresses at random and starts a TCP conversation, let's say. Once that conversation starts, they can signal that they're multi-6 capable, and they can exchange a complete set of locator IDs. Now the source knows all the valid IP addresses for the destination, and the destination knows all the valid IP addresses for the source. Once this is all set up, you can then insert the layer 3 shim, which includes a source upper layer ID and a destination upper layer ID. With the layer 3 shim approach, that key, so to speak, for the upper layer ID is keyed off of what the initial IP source and IP destination were. And again, I said there's many schemes of how to generate what to use for an upper layer ID. This is just one example. So what happens is at some point there's a failure. In this case, the destination's connection to ISP9 dies. So what will happen is the source will detect that the traffic forwarding is stopped, and this is done through the forwarding plane. And he will simply pick another locator ID out of the locator ID set and simply swap that as a new IP destination in the packet. When that packet arrives at the destination, he will strip off the IP header, and what's left is the layer 3 shim header, and that's what's delivered up to the upper layer protocol, your TCP conversation. So basically what happens is the IP source or the IP destination in the packet can change. These are the locator IDs. But that doesn't impact the TCP session because it's using an upper layer ID for its conversation. So the current IETF solution, there's a couple of important points to point out. First, that all the traffic engineering decisions are made by the source, not by the destination. There is provisions for sources and destinations to detect failover. There's a draft about that. They also say that traffic should load all links, and in the case of a failover, should only fail over onto working links. And again, failure detection is done through the forwarding plane. Some other things to note, though, is that without more specific routes, all destinations of a particular ISP can only be distance. So you can't say customer 1 of a particular ISP you want a distance, but not customer 2. Because only the aggregate exists in the routing table, which represents all of the customers of that ISP. Only all of the customers can be distanced. The same is true for reachability. Either all the customers are reachable in terms of the routing table information or unreachable. There's also no ability to do traffic engineering by destinations or by intermediary routers. So there's really no provision to dial traffic around. There's no provision to say, please use the shortest path from wherever you are on the internet, and there's no provision to specifically designate certain paths as secondary. It does provide for blind load sharing and failover, but it doesn't provide for a primary backup configuration, a best path scenario, again for some definition of best, or for the ability to dial traffic around, although that is a current IETF requirement. So what I'm suggesting is there are some additional IPv6 multi-homing requirements. We need the ability to designate paths as primary, secondary, tertiary, etc. We need the ability to instruct the source to use the best path, which need not be based on routing information. But it does need to approximate the shortest path between the source and destination. So my final point to hammer home here is the IPv6 multi-homing solution is not one that's useful for most of my IPv4 multi-home customers. And we need to provide IETF with the operational requirements so that we can get a solution which is useful. And in the meantime, we need to carefully consider inter-AS traffic engineering with regard to IPv6. So if your IPv4 networks you're currently doing traffic engineering or advertising more specifics, you're going to have to rethink how to do this in IPv6 until we have a better solution. Questions?
Hello. Hi, Mike. So this is yet once again the IETF designing something without a whole lot of operational input, and vendors are building stuff that will be compliant with the IETF specifications, and when it actually gets to the operators who buy this stuff, they're going to go, well, wait a minute, we want this and this and this and this. And they're saying, but there's no RFC. Right, so there's some sort of problem here as well. We've got time for a few questions, and I'm going to ask Scott if he can come on up, get ready while we take questions. So.
Okay, Rüdiger Volk, Deutsche Telekom again. Well, okay, Bill, you mentioned IETF doing things and, well, okay, not matching operator requirements. Jason, one thing that I was looking for regarding handling of announcement of more specifics for traffic engineering was the IETF took a very long time to define a new well-known community for dealing with this, and you didn't mention it. Are you supporting your peer?
My goal with this presentation was to simply point out that the traffic engineering we're doing today is not available in V6 based on that solution. It's theoretically possible to deaggregate the routes and get a solution that works just like it does in V4. And if we do that, we probably have to throw lots of hardware at the solution at some point. I'm not suggesting that's the way to go. I'm not suggesting that's not the way to go. There is basically a trade-off. You're basically looking at the difference between control plane state in routers, or if you have to share that information with the end hosts, and forwarding plane mechanisms for figuring out the information that you don't have because you don't carry the state. You could certainly do something that's ICMP-like to determine the shortest path between a host and the destination. I think that there are solutions that are out there that need to be explored. I just think that right now IETF is trying to solve the easy problems and not realizing that the solution is only a half solution.
Hi, hi, Barendra here. On your a few slides back when you had a packet header information there, and when the I guess if memory serves me correct, the locator ID in that source address, it for some reason goes offline, it picks onto the next locator ID. Now, in order to prevent from black holing traffic, is that address flushed out, or it's still there, kind of round robins?
Yeah, that's not currently well defined at this point.
Okay.
Basically, the important concept here is that the upper layer ID never changes, so the TCP session never dies. In terms of the set of all valid addresses that are exchanged between the endpoints, that does change from time to time. For example, if I'm multi-home to 2 ISPs and then I bring up a connection with a third ISP, I need to tell everyone there's a third locator ID which is also valid. It seems that the current belief in IETF is that if a link goes down, temporarily, that you shouldn't take it out of the locator set. But if it's a permanent disconnection, you've canceled service, you should take it out of the locator ID set. Does that answer your question?
Right, so there's some timeout, like a TTL or
I don't think that's clearly defined.
Okay.
I think right now what they're specifying is the destination should say, I'm no longer buying service from UUNet, don't use this locator ID anymore.
Okay, thank you.
Joe Abley. I think the problem with the SHIM6 approach not meeting all the current requirements of V4 multi-homing is not that the requirements are wrong, but actually that there are no requirements. The document was originally called a requirements document, but we couldn't get consensus until we changed the name from requirement to goals.
Okay, fair comment.
Tony Hain, Cisco. To follow on to that, the IETF didn't come up with all this stuff in a vacuum, right? The operators that were present as we were putting this all together said aggregation is paramount. You must, do strict aggregation. So that's what led to a lot of the decisions. If the decisions need to be changed, participation from this community needs to be at the IETF to make that clear, right? To the point about the multi-6 requirements document having to be changed, some of those requirements are self-contradictory, right? So you couldn't call them all requirements because you can't require things that contradict each other. So it's part of where we had to go is to say it's not really a requirement because you can't have both simultaneously. And there are trade-offs that have to be made here. This community has to come to consensus, and it can't be this room, it has to be a global consensus. And we can't just do it all in individual rooms in random places around the world. We have to come together, decide on what is the set of requirements we're really going to try to meet, and how are we going to prioritize that list. And that's, I think the problem you're running into right now is you've got a set of things you want to do which don't meet with other things that have been done in the past. The other thing, SHIM6 is a nice concept, and maybe in a decade we can think about doing something with it, but it's at least a decade problem. It's going to take at least 3 or 4 years to define it, and 3 or 4 years to get it built, and then another 3 or 4 years to fix all the stuff that it broke.
You are an optimist.
I'd say at least a decade, right?
Okay. Can we make these really quick because we need to not get too far behind?
Yeah, this is a comment, a question that came in from Jay Patel over the internet. What a surprise. He says, excellent talk, he liked it very much. I'm going to edit this a bit, as I said, and say he's commenting that you're not always fully responsive to questions about V6.
Fully responsive. Oh boy, that's a tough one. I think so. So I'd like to thank Jason for spending a few minutes. Get him at the break. Hunt him down.